Right, so don't forget with the linear and the exponential, the big thing is that we want to know how these different functions appear in the tabular representations. Well, the tables easily reveal the rate of change. Right? So with technology, creating a table is super straightforward, it's easy, but the bigger thing 100% is when I find the rate of change, I automatically know what? The type of function, right? So if it's linear in the table, we see a constant, what's it called? Constant additive rate of change. You definitely want that clarification there. With the exponential, what do we see?
Constant. Yeah.
Constant multiplicative. Rate of change. Y'all, please make sure in the future you silence your phones. Just can be distracting. When I look at that rate of change in the tables, do I just want to look at my outputs?
No, you gotta look at your input.
Remember, it needs to be the same over the equivalent inputs. So I will not do exponentials to you where it's something other than +1. At least not yet. We might get to that later this semester. But we want to notice those tables easily reveal the rate of change. That's a beautiful part of tables. And that's how you're going to know if it's linear or exponential. Linear has that constant additive rate of change, and exponential has a constant multiplicative rate of change. I bring that up because y'all have heard in the past probably that which function has a constant rate of change? Like, what did y'all hear like previous math classes? The only function has a constant rate of change. Linear, right? But that's kind of a misnomer, right? We see a constant over here, meaning it's the same thing every time, but with the exponential, it's just constant multiplicative. Alright? Some students refer to the graphs when they got to the next part. I do want to make sure that we all know how to do these. Actually, no, we'll get practice doing this in the new task. But I want to look at this with everybody, going back through these steps. Just to remind us, how do we go about graphing this data? What's the first button I always need to press to graph data? Menu, right? Anything, you weren't here yesterday, but just looking at those options, what do you think I'm going to go to graph a bunch of data? Graph entry / edit? Okay. Ishmael, you were here yesterday. Which option do I need to go to in order to graph data?
Scatterplot.
Don't forget, we're trying to graph data. Not a function this time around, but we're trying to graph data, so scatterplot. Okay, so notice how it's asking for the x variable and for the y variable. When it's doing that, this is why you need to pay attention and name your variables on the list and spreadsheets. Notice it's not just for your own benefit. Days, option 1, option 2, I need those for when it comes to the graph here. Does anyone remember what button I can press to bring up those variables really easily? Var. Number 9, what button is right above number 9?
Var.
Var. What's that stand for?
Variables.
Variables. Literally. So I click on VAR, and there's my variables. Day, or days, and option 1. Nope, I didn't want that in the same spot.
Oh,
That's not
mine's
that. Yes, because you haven't named any variables yet, have you? I'll help you do that later, okay? So there's days in option 1. I still need the second one. Days and option 2. Oh my goodness, I did that twice in a row. Yo, I'm sorry that I'm such a scrub this morning. There we go. Alright, so we can see option 2 there. Now, how many data points am I supposed to have? 30. I don't see 30 points. Zoom out.
Yeah.
So I'm going to hit menu again, and then Windows /Zoom for 4. Am I going to zoom out though?
No, you gotta zoom down.
remember, what we effectively have is data points, so I'm going to hit zoom data. Ah, there we go. Whew. So you tell me, are you taking $60,000 a day or starting with a penny and repeatedly multiplying by 2? You're taking that penny and multiplying by 2. So one of the details I want you to notice is a lot of us were distracted by that $60,000 a day, because let's be real, if I can make $60,000 a day, I'd take it.
Wait,
That's
so
more than I make in a year, huh?
So exponential is just breaking down the days.
Well, no. The exponential, right, has that constant multiplicative rate of change. So we investigated the points that we made in a table, and when we investigated the points in the table from the information given, we saw that it was constantly multiplying, right? Exponent, repeated multiplication.
I know here it was repeated addition.
Right, for linear,
Okay.
right? So I want you to notice, if we're talking about a linear function, what should we recognize in the graph? If it's linear, what shape should we see? A line, right? We need to be able to recognize, as soon as we see a line is a linear function. Now, does a line have to go in this direction? No. It could also do what?
Like that.
So that's a line?
Oh dang, that ain't no line.
That's not a line. What is that?
That's a curve.
That's a curve, okay? Someone said it a second ago. What'd you say? It can decrease. Notice that's increasing. You can also have a linear function that is decreasing. Okay? But that red, that's that multiplicative rate of change. And so that, remember, is our exponential function. What's the shape of that exponential function? And it's not just any old curve, right? The curve that Anthony was just referring to is this. That's a curve, but is that exponential?
No, that's a linear.
That's going to be quadratic. We're going to get to that later. But I want you to notice, right, we have this exponential curve like this. Notice how that exponential curve is flat and then it starts to exponentially increase. Similarly, you can have a decreasing one, like that. You need to recognize these different shapes. You can even have one that is like this. Notice how it starts out flat, but then it starts to exponentially decrease into the negatives. Or like this. Ooh, that is ugly. My bad, y'all. And you can definitely draw all 4 of these, or you could just make a note to yourself. By the way, does anyone remember what the name, or have a guess what the name of this curve is?
Which one?
These 4? Huh? It's literally just called an exponential curve, right? But you need to recognize that shape, because every time you see this shape, what kind of function do you have? Exponential, right? This is known as an exponential curve. It can show up in any of these 4, and it also doesn't have to approach the x-axis. Once we study transformations, we'll see how it can be translated up and down, things like that. But we want to recognize, as soon as I see that type of curve, it's exponential, which also tells me it has what kind of rate of change? Multiplicative, right? As soon as you know the rate of change, you know the type of function. But also, as soon as you know the type of function, you know the rate of change, right? They're all connected, and we need to be able to see each of those details. All right, I'm running out of room over there, and I want it to be nice and large, so I'm going to move over to here and keep linear and exponential. What's the next detail that we need in order to compare linear and exponential? We need the equation. By the way, what's the name? There's a bigger, an A word that we use for, there we go, right? I'm looking for that algebraic representation. And remember, that was in the objectives. So what was the equation for this linear function? Okay, so we know that the general equation is y equals mx plus b, where m is the slope. And how do I calculate that slope?
Changing y divided by changing x.
Thank you for remembering to make it divided by. Or I think I heard someone saying rise divided by run. Remember, those are just different ways to do that. Right? We need to define those things well. And And how would we see the y-intercept? Because remember, b itself is not the entire y-intercept, it's only part of it. How would we write the y-intercept? Say again?
0.
0. So that's the y-intercept, just that 0?
No, it's a point, so. It's a point 0 and x.
Not x. Well, first off, it's a y-intercept. But what letter up here is going to represent my y-intercept?
B.
Right, so the y-intercept is 0 comma b, and we just use the b for the y value of that y-intercept. So don't forget that. Defining those different features of that equation. But really what I was asking is, what is the equation for this linear function? We should have written that for number 2.
60,000 x plus 0.
Notice, I like the fact that you're including that slope and the y-intercept, or the y value of the y-intercept, just to establish y equals mx plus b. What's the one thing I'm missing though?
The answer. The y.
So, just put a y up here randomly,
Equal.
equals,
But yeah, that's the same
Slope
thing.
x plus b. Well, 0.
okay. Now,
Or
what's the function notation I could use instead?
F
f of
of
x.
F of x, right? I could use either one, that's perfectly fine. Alright. Now, before we get into the exponential though, because I haven't defined an exponential equation in this class. We've done linear quite a bit, right? And that's only one form of linear. But with the exponential, does anyone know the equation, the general one? Y equals a plus b to the x.
Yeah.
Okay, we'll get into that in just a second. Any other guesses? Oh, you could use f of x. Yep. Okay, so let's pause on that for a second. I want to come back over to this linear. Is there an alternate way to write this linear equation than y equals mx plus b?
Y equals a.
A.
You could put the 0 in the front and then do plus 60,000.
Yeah, so the y value of the y-intercept and then the slope. So I want you to notice, right, there's just an alternate way to write this. And we talked about this a few times in class. Because what is really defining the slope? How do we know where that slope is?
Because of the x.
Partially. But you can use variables other than x.
You said what?
What is really defining the slope? How do we know where that slope
Because
is?
there's two values.
Not
It's
just
the
that
beta
function.
x. Oh.
Being multiplied right there?
Yeah.
Dawson, why is it important that the b and the x are being multiplied? Partially. What else do we know about that rate of change? Michaela? Do you know what's important about the multiplication in connection with the rate of change? Not sure? Okay, so we may need to write this down if we're not sure about this answer. What did you say, Kelsey? Is it just that it's constant? Constantly adding, because how do we show constant or repeated addition in math? With multiplication, right? So we want to make note that the multiplication is what's defining that repeated addition. And so you just want to make sure that you understand in this one, A is the y value of the y-intercept, B is that rate of change, the slope. But let's look back at this exponential. Actually, let's come back over here. It was A, y plus. Not just because it's positive, because you could add a negative, which would be the same as subtracting, so y plus. Remember, you're thinking about linear. There we go, repeated addition, right? Which then we show with the multiplication. So, I'm talking about exponential. What have you already said for the exponential? Repeated multiplication? Not for exponential. Remember, an exponent is repeated multiplication. So I'm starting with an A, and then am I adding to it? I'm multiplying. So instead of plus, maybe a times? Would multiplication make sense if I'm repeatedly multiplying? Yes? Okay.
So now we doing area.
Why do you think area?
Cause that it looked like an area, farm.
Okay. So be careful. With an exponential, the variable is where?
It's from.
Typically, when we're dealing with area, we have an unknown length times, and I'm just going to say x again for an unknown width. Notice that's going to give me x squared. Does that make sense? So it's important to notice where the variable is. If the variable is in the exponent, it's exponential. But if it's x squared, that's something else. Make sense? Okay, we're good with that. So Anna, what's going to be a for this exponential function, right? We still have this table over here. Remember, the table is going to help us write equations. Any guesses?
For the second one?
Yeah.
0.1?
Reread that. 0.1?
Wait. Yeah. Wait. Yeah, 0.01.
0.01, right? And I want to remind y'all, I told you I like this equation for a linear because what is a here? The
Y-intercept.
y-intercept. So what's this a?
Y-intercept.
Technically the y value of the y-intercept, right? Because remember, I want a point 0, comma 0, comma what?
B. B
Is it going to be b here?
Oh, A.
And so that's why we have to be careful, right? Remember the y-intercept in this one is the a. We can't just say, hey, it's always at b. Okay?
Do you do times 2?
Times 2 raised to the x power. So in this case, b is my what?
B is your the rate of change.
So I heard slope. Is it slope here? What is slope?
Slope is rise or run. Rise divided by run.
Okay, slope is, we calculated rise divided by run. It is for a linear, but that's the name for what type of rate of change?
H linear.
Not just additive. Constant additive, right? We need to remember that slope is only for a constant additive rate of change. All right?
Constant.
Multiplicative.
Yeah.
Okay? So, I want to ask this really important question. What are factors of 6?
Ain't
Factors.
one.
There are factors of 6.
2,
2 and
3,
3. Or
1,
1 and...
6.
So what are you doing with those factors? You're multiplying them?
Oh, yeah.
So we call this multiplicative rate of change a constant factor. Right? That's the multiplicative rate of change.
Again, I just said 2 because it was multiplying 2 each time.
Correct. So we're repeatedly multiplying by 2. We started 0.01, repeatedly multiplied by 2, x number of times. Alright. We're going to wrap this up in about 2 minutes. We're almost done. I need y'all to finish taking these notes so that we can move on to a new type of function. And so, the last thing, so remember, does anyone remember what the very first objective was? It was all about differentiating the, something about linear and exponential, it starts with an R, rate of change. And we've talked about this heavily at this point, right? So, the rate of change for a linear function is what? Constant additive. Called? Is slope-intercept just the rate of change?
No.
Remember, slope-intercept is an equation of a line, right? Or one equation of a line. What is the name of just the rate of change?
Slope.
Slope. But, and so we just have to be careful. Y'all are just programmed. Every time you think slope, you just say slope-intercept, right? But it's just the slope. Okay? Whereas for an exponential, the rate of change is Constant multiplicative. Called what? Alright. That's a lot of writing, I know. Get those final notes down. Miss Courtney, can you pass out the Gold Rush task while they're writing these final notes?
Can you know what our next test is?
Or what?
Test.
I was trying to shoot for next Friday. It won't be next Friday. It'll be a little bit after that.
Are we just financially unprepared?
Yeah, financially unprepared. That's it. Okay. Before I move forward, I do want to point this out. Last, very last detail. Actually, two last details. I want you to notice we need these notes in our notebook because if we see that constant additive rate of change, we automatically know it's what type of function? Linear. And if you know it's linear, you know a general form for the equation, right? Similarly, if it's exponential, you know it's constant multiplicative, which gives you a general equation. If you see this curve, you automatically know it's what? Exponential, which tells you a lot about the rate of change and about the equation. So one representation can tell you a lot of information about the other representations. That's why you got to know each of those differences. If you didn't fully take these notes or you're forgetting details, remember these videos are going to be on YouTube. Now, the last thing is, how can I check to make sure my equations are correct? Say again? Okay, I can plug in some numbers, right, to check. There's an easier way with calculators, though.
Put it in to see if it's true and false.
Well, and so you're talking about plugging in a value, right? Okay, but that's only going to check one point at a time, right? Now, every point should make the equation true, but what about if I graph those equations? What should I see? Well, not just the curve. Let's do the 0 plus 60,000x.
Shouldn't have been like, I was just gonna say replicate the same one.
What does that line do?
Highlight.
Doesn't just highlight, it goes through the points. If I have the correct equation, that line should go through all those points because that means all those points is making that equation true. Let's check the exponential. So did I get the correct equation? I bring this up because on this new task that we're starting with Gold Rush, you should not have to ask me or ask Miss Courtney if you have the answer right. We're going to support you to get there, but if you put points into the calculator and make your graph, can you type your equation in to check to see if your equation is correct? Okay. I want you to become independent thinkers, meaning that you are able to identify, is this correct or not, to play around with ideas and make sense out of the mathematics. So here's Gold Rush task. This is what we're going to spend the next day on, roughly. All right? With Gold Rush, actually, sorry, I should have paused for a second. Does anybody have any questions before we move on from linear versus exponential?
No.
Okay, you don't. Anybody besides Shakila? She's always on top of it. Anybody else have any questions? I would love to answer those questions. All right.
No.
Thank you. All right, let's move forward. Now, I will say this. Do we probably need some practice with these ideas?
Yes, definitely.
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 We will get that practice next week once we learn a little bit more about quadratics so we can work with all three at the same time. Okay? So, objectives. Remember, it's hard to learn what you're supposed to learn if you don't know what you're supposed to learn. So, first things first, with quadratics, we need to learn about the what? Rate of change. There's a different rate of change for a quadratic, right? Linear, If it's constant additive rate of change, you know it's linear right away. If it's constant multiplicative, you know it is exponential. Well, a quadratic's gonna have a different rate of change, so we need to be able to find it. And similarly, quadratic functions are gonna look different in tables, graphs, and algebraically, those equations. So we're gonna try to investigate that, right? I will remind you, what do we see most easily in the table? The rate of change. That's something to keep in mind, right? So we're seeing that tables are really useful for rates of change. Graphs show us shapes. Equations can represent anything. And so we're going to begin writing explicit quadratic equations. And I will say this is an objective from a previous class and I forgot to modify. Y'all don't need to worry about explicit versus there's something called recursive. We're not getting into recursive. So just writing quadratic equations. Here's gold rush, okay? In the 19th century, actually, before I do that, what do y'all know about the gold rush?
Nothing.
Nothing?
I know. Okay, it was
I hear a lot of people talking. I love the enthusiasm, but let's give people an individual chance to talk. I first heart Sharnavia, and then I'll give other people a chance to talk.
It was like everybody discovered gold and started coming to the US.
Everybody discovered
Not
gold?
everybody.
I wish, man. I would love some gold.
Like,
Right.
from Europe.
Okay, so discovered gold.
Well, it was a rumor going around that you can find gold in California, I think. Was it in Cali?
Yeah.
Yeah.
Sound about right, California?
And then everybody just rushed to California to try to find gold.
Yeah, because if there's gold, I want it, right? That makes me lots of money. As a quick reminder, I do want to point out, I hear a lot of students involved, but, and by a lot I mean, I would say like 6 or 7 students are really engaged in the conversation, but maybe a little more than that. I want you all to be involved. The more you talk, the more you're going to learn. You need to get involved. I can't force that upon you, but I do have that active collaboration that I'm always scoring, and this is a part of that active collaboration. Engage, talk, share ideas and thoughts, okay? So, yeah, rushing out to California. And so a lot of times you would have to dig for that gold, or there was pan mining for gold, I believe, where you take a pan, you dip it in the water, and you sift around trying to find flakes of gold and stuff like that. Well, here's the thing. That takes a lot of work, right? So, in this context, in the 19th century, many prospectors traveled across North America to search for gold. A man named Dan Jackson owned some land where gold had been found. Instead of digging for the gold himself, he rented plots of land to the prospectors. Why do you think he did that? So they did the work for him, right? And here's the thing. Is he still going to make money?
Yeah.
Notice that's guaranteed money. He doesn't even have to do the work. He rented out his land and made money off those people. Man, the chance, anytime you can buy land, go for it, right? Always be working long term to try to be able to own plots of land and own what you have instead of rent. I promise you, you'll be better off for it. That's a small side note for today's world, okay? So instead of digging for the gold himself, he rented plots of land to the prospectors. Dan gave each prospector 4 wooden stakes and a rope measuring exactly 100 meters. Each prospector had to use the stakes and the rope to mark off a rectangular plot of land. So, are there lots of different rectangles that you could create?
Yeah.
Yeah? Assuming each prospector would like to have the biggest plot, pause there. Why would the prospectors want to have the biggest plot of land?
So they got more chances.
More area to lead.
Yeah, you got a bigger plot of land, you got a bigger chance for gold. That's an important thing to establish, that better chance to find gold. So what should the dimensions of the plot be once he places his stakes? I need y'all to pay attention to this because this is where students got lost in previous classes, or previous times I've taught this lesson. When you place the stakes and you create different dimensions for that rectangle, that will affect the area. Somebody give me one set of dimensions that we could possibly use. Any guesses? So length and width, I mean like, we have how much rope?
100 meters.
100 meters. We only have 100 meters. We want to make the most use of that as possible, right? So what are some options for, say again? So let's look at that. This is important.
75.
Hold on, you're just shouting things. Hold on. I want you to look at that again.
That's 200.
Say again.
I was only doing 2 sides.
You were only doing two sides. So this is a detail where a lot of students get lost and they miss. Okay, if you say 50 by 50, well, that's 100, but that's a total of 200, right? So we can't do that. You do want to pay attention to this. Okay, so what about this? Let's say we have a really skinny rectangle. Let's say that this is 2. Anyone know a different number I could do?
75.
No. 2, and then what would the other dimensions be?
The other side.
The other side would be 2.
40?
So if I do 96 here, isn't that already 100?
Yeah.
But I still need another 96 across.
46?
So if that's 46 and this is 46,
It's 48 on
48,
both sides.
48 on both sides. Notice this would be 2, 4, 50, plus 46 is only 96, right?
Oh, so you're gonna do 48.
48? Yeah. It's okay. So I want to point this out. First off, what are the different mathematical representations that you can use? We already talked about a few of them. Tables, graphs, algebraic, and we haven't talked about those last two you said, right? We've got a verbal representation, words. This is a very simple pictorial representation, and you can use this to help you get started. Remember, we want to focus on tables, graphs, and equations, but this can help you get started because you might be able to find some patterns. So from here, what would the area be? Remember, as for area, remember the perimeter, the distance around is 100. How would I calculate the area here?
Base times height. 96.
So we would do base times height for area, right? So 48 meters times 2 meters. Notice it's not just 96
Square.
meters squared, right? Meters times meters is meters squared, okay? So, what about, I'm going to make it even skinnier. So 1 meter. What would the other dimension be? What would the base be?
49 and 49.
So 49 meters here?
Yeah.
And so what would the area be?
49.
49 times 1.
Not just times 1 meter.
49 square.
So 49,
Meter square.
oh, meters squared.
Yeah.
So y'all tell me, which option are you going to go with out of those two?
I'm going with that 48 times 2.
That 48 times 2, 96? So notice, do these have the same perimeters, the same distance around?
No.
Listen to the question again.
Yes.
Same distance around.
Yes.
That is how much around? 100. That's the full length of the rope.
Oh, yeah.
How much of the round is it here?
Same.
The same, right? But the areas are different, right? So what I'm asking you to do is to figure out what's going to happen